Alright guys, let's talk about question 5 now. In this case, they've also given us a dy dt equation, which represents the differential equation for y. Y is the quantity that changes with time. And now they want you to find the stability, or actually the steady states of this differential equation and comment on their stability. So what you can do is, once you find the the steady states, all you gotta do is put it equals to 0 and solve for the y values. In this case, you're gonna get 3 y values. I wrote them in the increasing order like this. There's gonna be -2 coming from this factor, +2 also coming from that factor, and 0 coming from this factor. Okay, so now once we have this, let's use the graphical way to analyze the stability of this. What you can do is you can either sketch these things or just kind of use Desmos to get a picture of it. Once you have this scenario here again for the phase line where dy dt is just whatever this side is, and this x-axis represents the y function here. When you plot it, all you're going to see is -2, 0, and 2. So now testing the stability again. If you are at -2 and you go a tad bit back, the derivative at that point is above the axis, so it's positive. It wants you to push back and increase the value. So you're going to come back to -2, sorry. So you have these arrows pointing this way. If you are a tad bit to the right, which you mean you're going to be a positive value, a little bit bigger than -2, what happens is the derivative at that point is negative, which means it wants you to push back. So when you make these arrows, you can confirm that this is a stable steady state. Or you can look at the calculus way as well. If you draw a tangent, the tangent is pointing downwards, which means the state is stable. Now at 0, if you draw a tangent, it's unstable. Or you can do the test as well. If you're a little bit before 0, the derivative is negative. It wants you to go further back to decrease the value. So the arrows are going to be pointing outwards. If you're at 0, you move a little bit right. The value of the derivative at that point is positive, which means it wants you to increase the value from wherever you are. So you're going to go diverge on both the ends of 0, which makes this one an unstable steady state. Again, at 2, you can do the same analysis or draw a tangent. What you'll see is this point, tangent positive, push you back in to increase. If you're at some point bigger than 2, tangent negative, I'll push you back here. Okay, which means this state is also stable. And that's how you can comment on their stabilities using the graph. Okay, question 6 is also a same approach, but instead of drawing a graph, I'll take the calculus approach as well. The key factor here that we saw was for a stable steady state, derivative before this must be positive and derivative after that must be negative. So remember this rule. So if you have that kind of scenario, you're going to have a stable steady state. Okay, so let's test this here. When you're given this equation of dy dt, the only way the steady state is going to be happening is when y is equals to 0. So when y equals 0 is the only steady state. Let's talk about the stability using the calculus. So if you pick a value for y that is less than 0, which means you're a little bit before the steady state, what we observe is dy dt is going to be positive. How, you ask? When you go back to this function and you plug a negative value for y, the negative y and this negative will make it positive. However, the bottom is also y squared, which is always positive, which means you're always going to end up with a net positive result for dy dt. So if you're a little bit before the steady state, the dy dt is positive, which means y will increase back to 0. Okay, because it'll push you back. If you're a little bit before, it'll push you back up because you're going to increase. How about if you are a value above 0? What's going to happen at that spot? When you're having a value bigger than 0, you plug it in. This is going to be positive. There's an inherent negative sign in front of it, which makes the whole dy dt equals to less than 0. Which means the y will decrease. So if you're a tad bit bigger than y, it wants you to push back. So you'll decrease back to 0, which means both left and right approaches 0, you have a stable steady state. This was the calculus approach. If you guys don't get this one, it's completely okay. You can again sketch this graph in Desmos and then see the same test analysis with little arrows and get it from there. Okay, question 7, they already gave you a phase line diagram. So we have a bunch of steady states here. I'm going to just zoom in here so you can see it. The steady states are the zero crossings of this graph. So in this case, it will be -3, -1, 1, and 2. So we're going to be observing the stability of these states even though the question is not asking us to do it, but just for the practice, we're going to do it. So again, two ways. You can draw a tangent at the state. If it's negative tangent or downward sloping, it's stable. So stable, unstable, stable, unstable. That's one way. Or you can do the arrow analysis as well. Go a little bit back, derivative is positive, it's going to increase, so come back to this point. Go a little bit ahead, derivative is negative, so it's going to decrease, come back to wherever you started. So this is a stable state. And then if you draw the same arrows analysis for the other ones, you will see the same matching result. So it's completely up to you how you want to solve it. No preference here. Okay? Now question 8 is again same textbook style problem. Now in this case, the differential equation is cos of y. So steady states are where cos y is equals to 0. And now they've given us a range from -5 to 5, which is going to be like in between 2 pi to -2 pi. So we're going to draw a piece of the cos graph. So you got to put it where cos y equals to 0. There are only the multiples of pi over 2. If you don't know that, it's okay. You'll learn that at the end of this course. So don't worry much about it. What you can do is for the meanwhile, use Desmos to plot it. Okay, so when you punch it in, you saw the 0 crossings between 5 and -5 happens at these locations, which are going to be -3 pi over 2, negative pi over 2, pi over 2, and 3 pi over 2. There are these ones respectively. And then this is going to be pi over 2, and then 3 pi over 2. So you got to label all these in the increasing order, and then you can test the stability using the same way. If you draw a tangent at this point, downward sloping, which is stable, tangent at this point, upward sloping, unstable. Let's do the arrow analysis here. So if you go back here, the derivative is positive, so you're going to increase back. If you go a little bit above this, derivative negative, you're going to come back. So this is also stable. And then this case, if you go back, the derivative is negative, so it'll push you even further back. If you're a little bit bigger, the derivative is positive, so it's going to even further push you away from it. That means this is unstable, which also matches up with the tangent line analysis. Okay, and that's how you answer question number 8 for all the stabilities and stuff. Now question 9 is again with the slope fields. What they're trying to do is they've given you the footprint the solutions will follow, as we talked about slope field does, and now they want you to start at different initial points and see how the solution goes, kind of like sketch it out. And then once you sketch it out, they want you to approximately find the values where the given points are. Okay, so the first time they want you to start at 0, 0. Okay, so we're going to start at 0, 0. And if you start here, you know the slope field is just going to be steady here because 0 is a steady state of this differential equation. As you can see from the slope field, it's always going to be 0. So if a solution starts here, it's always going to be a horizontal line like this. So if you're asking for the value of y of 1 and y of -1, so you observe the value at 1 and -1, it's always going to be 0. Okay, so that was an easy catch here. Now if you start at 0, 1 here for this line, which is going to be this point, where you're going to end up is you got to follow the slope field. So if you follow these lines here and you go along with it, you're going to get this side is going to look something like this. However, the other side, when you have to see, you got to go backward and keep on increasing like that. Okay, it could be fine, it could be okay if you're trying to like draw. It doesn't have to be exactly the same way, it just got to have a flow of the solution. Okay, so the solution that passes through 1 will start here, go down like this, and all the way settle down to 0. Okay, so in this case, when you're trying to approximate the value of 1, you'll see that this is going to be like 0.25, somewhere closer to that. And if you approximate the value of -1, you see the function has this value here, so 2.5. Same analysis that you can do for the last part of this equation as well. When you start at this point now, and now the function following the slope field will just go like this, and at the back will go down like that. So essentially they're symmetrical of each other. Okay, this one goes decay from the positive, this one goes down like that. So whatever values you got here should be symmetrical in the other, but with the negative sign. So in this case, y of 1 is just negative 0.5, and then y of -1 is going to be this value, which is negative 2.5. And that's how you solve question 9. Now, question 10 is not based on differential equation. This is just another regular optimization problem. So in this case, they've given you a function r of x that's just ln of some function L times some function M divided by X. So first of all, it's a better choice to kind of like go through and analyze this by simplifying it. So we start to simplify. Ln of two things that are being multiplied could be written as ln of the first thing plus ln of the second thing. I did that, and then you can separate these two into two different entities here. Once you have these two separate entities, you've given the L values, you're given the M values. So you punch it into the functions and simplify it a bit further. So ln of e to the power of something is just that something itself because of a fact and property of ln. So that top becomes just negative 0.14x. Okay. However, in this case, you got to treat ln 3x to the power 1/2 as again something being multiplied inside a ln, where the first thing is 3, the other thing is x to the power 1.5. So you separate that using the ln property, where ln of the first thing plus ln of the second thing. The ln of the second thing would be ln of x to the power of 1.5, but you can bring that power down and write it like this. After this point, it's just random algebra, which I encourage you guys to try it for yourself. Okay, where these x will cancel each other out, you just simplify a little bit. And then from this point onwards, all you got to do is to maximize this r of x, you got to find the optimum x, which is a critical point. So all you got to do is take a derivative of this function, which we did here, and isolate for x and solve it. So when you move it here, you're going to get this step. You got to see it's the only numerator that's going to make it equals to 0. So you isolate for those. You keep on doing the simplification. You're going to get ln x equals to 1 minus ln 3 over 1.5. To further isolate it and solve it, you can follow the steps that I did or do it yourself as well. The optimum x is just whatever the value is going to be. Okay, and that's an optimization problem. It has nothing to do with the related rates. Okay, so now we're going to talk about question 11. Question 11 is a differential equation. Now in this case, the reason why I told you the calculus approach sometimes helps you much better. Let's see that how here. So when you're here, you're given this very weird kind of to the power 4 differential equation. Now to find steady states, all you need is wherever this thing is equals to 0. So you got to factor it out. I factored out a y squared from it. And then you can break down the inside quadratic into two factors, 8 and minus 4. So essentially you got 3 steady states here, negative 8, 0, and 4. So now you got to see wherever the function's increasing or decreasing, so the solutions are increasing or decreasing. All you got to do is check the sign of dy dt in the intervals given like this you did in the curve sketching part of the course. So you got to label all these things, negative 8, 0, and 4. And now in this interval, if you pick any point and plug it in there, you're going to end up with a positive result. Between negative 8 to 0, if you pick up any point and you plug it in there, you check the sign, you're going to get a negative result. From 0 to 4, if you pick up a point and you plug it in there again, you check, you're going to get a negative result. And if you pick any point above 4, you're going to plug it in there, you're going to get a positive result. So from this, you can say it's increasing in these two intervals and decreasing in these two intervals. So you can combine them using the union notation and write them up like that. Very straightforward. Nothing crazy stuff here. Now, the last question tells us about population of something. I don't know what that is, but yeah, it's talking about a differential equation which tells you the population given by this equation right here. Now, first step is always to find steady states in this analysis. All you got to do is put it equals to 0. So the first factor that you can figure out is p equals to 0 or this whole thing equals to 0. So when you equate this thing equals to 0, the other steady state that you found out will be 2 multiple positions. Okay, if you follow the algebra here, that's a squared here. So when you move the stuff around to the left side and you take a square root of 400 is going to give you a positive 20 and a negative 20. So p minus 50 could be either positive 20 or negative 20. So when you move them, you get respective steady states to be 30 and 70. Okay, once you have the steady states to actually test for the stability, you can use the phase line. So what I did is I just became lazy and I plotted this in Desmos. The graph looks like this. Okay, once you have this, and we can just cross validate our stable steady states and unstable steady states. We're just looking at it again, the same analysis. You can draw a tangent here, downward sloping, which means it's stable. Tangent here, upward sloping, which is unstable. Tangent here, downward sloping, so that's a stable steady state. So this is how you comment on the stability. We can do the same analysis that you did in the previous parts as well. And now the carrying capacity is also by definition the largest stable steady state. We got 0, 30, and 70, out of which 70 is the only steady state that's stable. Okay, so that becomes our carrying capacity. The threshold value, however, is a value before which you're going to go to extinction and after which you're going to go to the carrying capacity. So let's say if you're at 30, if you are at a point before that, you jump a little bit before that, the derivative is negative, is going to push you all the way back to the next steady state, which is 0, which means your extinction is happening. But if you are a little bit on the right side, you see the derivative is positive, so it's going to push you even further, all the way to the next steady state, which happens to be the carrying capacity. So in this case, the threshold value is just 30. Okay, and then the last part of this problem is to match up the graph, which you can easily do from there. I didn't have the access to the pictures, but yeah, I made a similar diagram. You can just very easily click on the link and match the one that works the best. Watch out, you should have closed dots here because they're stable, and an open dot here because that's unstable. Arrows should be the same, and the function should look like this as well. And that's it. I hope you like it.